Hello, good morning everyone. Welcome to the class ECE451 Control Engineering. Today we will consider the second method about the digital control. Okay. It's ECE451. This is a 13-week Wednesday's class. Alright. Okay, for digital control, so the basic idea is we try to realize some part, usually is controller of a system, by a digital way. Right? We suppose for these controllers, so like this is a D of S. Now we want change this. This is analog way, right? We change this in a digital way, so we need to work like this. We do a analog to digital converter. Then we have okay, like this is a E of T. This is a V of T. Then here's a E of T. Then after we take sample, we have E D of N. Right? This is a discrete time signal. Then we have a system. This is a discrete time system. I use the same D, but D with D of Z, right? By Z transform to describe a discrete time system. And then this output will be some VD of N. Then we go back to the DA converter. Right? This is AD, this is DA. Then we have RCV hat. Actually, it's not exactly as same as that one. V hat is a kind of approximate with V. And for both these and these, we need a T. T is the step to take sample. So for this part, this is just E of NT. And this one, V hat of T, we hope it is close to VT. Right? And VD of N, it is just V hat NT. Or maybe a little bit different, something like that. Okay. So this is a digital one, right? Digital one. So we realize these analog controller by a digital way. Okay. The last time we gave a method we call the testing method. We just D of S, we go to capital D of Z. This is just the D of S, but replace S by 2 over T times 1 minus Z to negative 1 over 1 plus Z to negative 1. Like this. We just make a kind of a transform, right? We replace S by this one. Then we have function on Z. This is a dd of Z. Okay, just like this. And we have name for this. We call this is a bilinear approximation. Right, bilinear. So S go to T over 2, 1 minus Z to negative 1, 1 plus Z to negative 1. Yeah, sometimes you want to write this as 2 over T. I just time T in both numerator and denominator. I have Z minus 1 over Z plus 1. Okay, same thing. Okay, today we consider another method. In this method, we use the zeros and the poles. So we call this as matched pole zero method. It works like this. It works like this. Suppose we have a transfer function d of s, which is 1 over s plus a. Then we perform inverse Laplace transform. We can have this is an impulse response, right? This is impulse response. We have e to the negative at, which is an impulse response. Okay, then we take sample. Take samples with that capital T. I need a capital T, right? This one, I have capital T. So we take sample of this. Then I have e to the negative a t n, which is e to the negative a t to the power n. Right? Okay. Then we go back to the transfer function, but this is discrete time case, so I do the z inverse z transform, just z transform, this direction, z transform. By z transform, then this one will give us 1 minus e to the negative at z to negative 1 over this. Alright, look at this one. Okay, then you see, okay, this is a d of z. For this case, no, I just write in this way. Okay, so this pole is negative a. Right? This pole is negative a. And this one, pole is e to the negative at. Okay, so we work in this way. Every pole or zero of the analog system, we replace the zero or pole by this number. Then we have the system in the for the discrete time, right? For discrete time signal. So the method is described by this way. We have three steps. First one, okay, replace every s plus a by z minus e to the negative at. This one, according to negative a, is zero or pole, right? Negative a is zero or pole. Depending on this term is in the numerator or denominator. Right? And similar, now is e to the negative at is zero or pole. Yeah, similar, depending on it is in numerator or denominator. Numerator is zero, denominator is pole. Then second step, if after replacement, actually before the replacement, doesn't matter, the order is same. Okay, we check the order of the numerator. If this is smaller than the order of the denominator, then add z plus 1 to the numerator. Okay, the third one, we want d of s and d of z. They will have same DC gain. That is as is the steady state if input is us of t or us of n, right? For continuous case, you can use any t. For discrete time case, the time must be integers. The steady state. This one, okay. So this is the method. This is the method. This is the method. Now I need to explain something. Okay. This one is fine, we know how to do it. This one is also fine, we know how to do it. Then what is the DC gain? DC gain. We have the, we also call this the final value. Final value. Final value for f of t and related with f of s by Laplace transform. This is a continuous case, analog case. Then the final value limit when t go to infinite f of t or equal to limit s tend to be 0 s times f of s. Okay, this is one. This one is for the analog signals, continuous time signals. Then for, okay, I still use f, but fn. This time related by a z transform. Then we have capital F of z. Okay, this time limit. Let me see. Every limit n go to infinite, right? N go to infinite. F of n. It will equal to limit. Now is z go to 1. Then times here's 1 minus z inverse times f of z. Like this. The final value. Then the DC gain. For d of s, for f of s, okay, this is in generally, not just for our computer, in generally. For this one, for fs is us of t, then here is y of s, then yss. This again in this one, yss, it will be limit s tend to be 0. Okay, here's s times capital Y of s, right? Now the f should be capital Y. And capital Y is f of s times us of t. It is 1 over s. Okay, this is y of s. Then you cancel. So this is you can say it is just f of 0. Alright. And for this again, for this discrete one, f of z. This f might be different. Just this is in generally I use a capital G. Okay, G. Then this side is still us, unit step, and here you will have y of n. Then this again is also the steady state of this y, and it is limit. Now is z tend to be 1, and it will be 1 minus z to negative 1 times g of z times, okay, this one us of n, it is 1 1 1, right? All of them are 1. Here's n equal to 0. This one by z transform, you will have 1 plus z inverse, z negative 2, and so on. So this is just 1 minus z to negative 1 in denominator, and numerator is 1. This is this one. Oh, sorry. Right. Yeah, we want the steady state of the discrete time system, right? Input is unit step, and what is output? When n go to infinity is a steady state, right? Steady state equal to this one times this one do z transform in this one, so go to here. It's 1 over 1 minus z to negative 1. You see, these two cancel, and z tend to 1, so this is a g of 1. Okay, so we want these two are same. This is the third step of the method. We want they have the same DC gain. That means d of 0 equal to dd of 1. That's this one. Alright, the method is clear, right? Now we study an example firstly. I just use d of s equal to 1 over s plus 3. We have this before, right? Last time we use this as an example for the testing method. Now let's do the similar thing. Okay. This is my testing.m. Let me open this. Okay, my testing. Alright, let me save it as a new file. Save as today is third week, right? 13 week, sorry, not third week. 13 week. So it is it's a ECE451. Then it's a 13 week with this class. Okay, just like this. Save it. Alright. This is it's s plus 1 and s plus 3. Okay, same thing. I use this one. Let's do use this one. Use this one. 1 over s plus 3. Alright. Then the GD, this is a testing method. Okay. Now we use a different GD. GD were equal to, okay, I gave GD1 firstly. This one we will replace the zeros and the poles by this method. Now numerator is 1, so it is still 1. And the denominator is s plus 3. Now I will replace it by z minus exponential power of t is given. Okay, it's a negative a times t, so negative 3 times t. Am I good? The formula. So s plus a were replaced by s minus e to negative at. So now it's plus 3. So here is minus e to the negative 3t. Okay. Now a is 3. A is here. A is here. Okay. So I have GD. But then we need to check the final value. Final value. Let me do it. D1 DD, I just write DD. DDS, I need this no zero, and the pole is this one, e minus e to the negative 3t. And here we need a number. So I say this is a k. then d1 will equal to d0. Right, we wanted the DC gain the same. So this gives us z is 1. I have 1 over 1 minus e to the negative 3t as a k equal to, this is 0, is 1/3. S is 0 and 1/3. So k is, okay, k is just this one. Alright. K is, it is 1 over 3 times 1 minus e to the negative 3 times t. Am I good? 1/3. Okay, just this one divided by 3. I don't need right, so looks confused. This is in numerator. This is in numerator. Divide by 3. Alright. Divide by 3. Then our GD will equal to this k times that 0 in the pole, so that is a GD1. Okay, so this is our GD. And then we can, in figure, we will see this one, this one, this one, and the GD2. Okay, so here we also have a method. This is just the match the PZ map. I think just match the PZ map. Oh, this is not match PZ map. They have another match PZ map. I just put it. Okay, maybe it works. I'm not so sure, but I think they use a different one. MZP match the 0 and the pole and 0, PZ or ZP, which is in the front. C2D. C2D. Oh, just match. Oh, okay. Match the pole 0 method. So it's an MPZ. Match. Okay, here's match. But here's a match. Okay, then let's run it. Which one? In line 12. In line 12. Oh, I need more. This one. Okay. Is it good? Then F5. Oh, now it works. It will run for a while. Okay. Yeah, something wrong, I think. Actually, in MATLAB, this function it will use name is modified matched method. So here, if we just look at this graph, we have the blue one. This is the continuous one, right? The red one, this is a discrete time one. But we have two, so they are combined. They are totally same, but they should be different. I think I got something wrong. Am I good? Let me check. Oh, I forgot that. Yeah, sorry. We needed the second step. Second step, we need this one, right? We need to add if the order of the numerator is smaller than the order of the denominator, we need to add z plus 1 to the numerator. So here we have this one. Then yeah, we cannot work like here. We need this. So d of s d of s, it will be some k times s plus 1 over z plus 1 over z minus e to negative 3t. It should be this one. Then we do the final value should be same, so d1 equal to d of 0. We have k times, here's 1 plus 1, there will be 2, and here's 1 minus e to the negative 3t equal to s is 0, get 1/3. So k will equal to 1 minus e to negative 3t over 6. Okay, so we need this one, this k. Okay, so let me change here. GD is this one, but now this one should be z plus 1. Z plus 1. Alright. And the k will be 1 minus that over 6. Over 6. Alright. This time it should work. Let me see. Okay. You see, the red one is given by the MATLAB. Actually, that is a modified matched pole and zero method. And now is just the pole and zero method is this green one. It's a green one. Okay, this is a green one. Alright. Yeah. Okay. Okay, this example is done. Matched pole zero method. Okay, the method is quite simple. You know it, then you know it, then you can do it. But here we want to know more details. We have a relation, right? Every pole at negative a, then we have a pole in the z domain is e to negative a. So this gives us a relation. Actually, 0 we use the same way, right? Pole zeros we use the same way. So this way we have a relation between the poles and the zeros in S domain and zero domain. So we make some details, try to understand some details about these correspondence. So we have S and Z relation in the matched pole and zero method. So every S, if this S is a pole or zero, a pole or a zero, then we go to another one, is a Z. Z is e to the at. This one is also zero or pole, right? Both are zero or poles, and they are related by this relation. So what is this? What is this? Now we can have a look. If S equal to j omega, actually in S domain, we have this side, they are the stable poles, right? Poles, unstable poles. If you have any poles here, the system is unstable. And here's the stable poles. If all the poles are located in this side, the system is stable. And here is the marginal poles. Right? Yeah. The marginal poles. Okay, for the marginal poles, by this way, we are according to a Z, there will be e to the at. A is j omega, right? A is j omega, so this is j omega times t. Now what is this? This is according to unit circle, right? This is z domain. Right, this is e to the j omega t. It is a circle. Here's a 1, here's a negative 1. So this line go to a circle. And then the S-plane I separate it as two parts, right? The stable side and unstable side, left and right. Then here, the left side, where are those coming from left side, and where are those poles coming from right side? Alright. Now we can do some more calculation, but let me use my lab to do it. Use my lab to do it. Okay, this is the first part is just for the method. Now we go to the second part. Not this one. My lab thinks this is equal. I put this. Okay. Then I want to see. I have a S. S equal to some A plus J times omega. Alright, omega is in the middle, so I think like just from 0 to, for example, to 3. Okay. Oh, this is not nice. Right? The same key. I need to shift it, lift it. 0 and to 0 to 3, and I give a step 0.01, and S equal to A plus, okay, A is a number. So like for example, if A is 0, then this will give us the marginal point, right? For all the omega, this S, they are run along the marginal line. They just imaginary part, no real part. So for this S, and I want Z. Z is what? Z will be exponential power of negative S times T. Do I need a negative? Oh no, that is S plus A. Okay, so this is this one, right? S plus A, according to Z minus e to the negative AT, right? And the pole at S, then pole will be e to the ST. Right? Here the pole is negative A, so here's a negative A. It's negative A, just the pole. So pole is S, here will be S to the T. Right? S plus A go to this one. The pole is negative A. Then pole is S, here's a e to the ST. Right? Here's a pole is negative A, here's a negative A. So pole is S, here's S. Okay, so we have this one. So S go to, okay, now I have a P, I have a Z, right? I have a P, I have a Z. Let me plot it. So plot, I give two graphs. Figure, do we need the first figure? Okay, I use figure 2 and figure 3. Figure 2, I just plot S. Now S, we have real part and real part of S, and imaginary IMG or IMAG, imaginary of S. Let me see, this will be a straight line, hopefully. Okay, this is figure 2, and the figure 3, I will plot. Now it's Z, so similar, I use real part of Z and the imaginary part of Z. Alright, that's wrong. Something wrong. So in the line 27, line 27 is here. Oh, okay. And then line 37. Let me say this one. Okay. All right. What it is? The first one is a step response. Then second one, okay, this one is good. This is just 0, right? This is the imaginary, the line with imaginary axis. And this one, go to e to negative 30. I got something wrong. E to the negative. Oh, not real part. Imaginary part. Exponential power of s times t. S times t. Omega is 0 to 3. Oh, what is a t? My t is too small. I make it large. This one, yeah. So this, you see the graph here. The unit is 10 to the negative 3. So very small. Okay, run again. All right, this time looks better. Right? This time looks better. E to the. But can I have more? If I use omega with large omega, like 30. Oh, okay. Yeah, this time is good. Yeah, now that I use omega large. So it should be unicircle, right? As I said, unicircle. It should be unicircle. Now in the graph 3, it is unicircle. The omega n and when the omega and omega increase, this curve will turn around like this. Go to here. If omega even larger, now it's omega. Omega is now it's 30. If I use 30, like 40, then this point they will keep going up and then go back to the old obvious. Yeah, this will turn around like this. So this is the marginal line, and then. Okay, so this line, according to this line. Alright, now if I choose this one and this one, where are they? Alright, so here I can give 3 lines. I calculate S and Z, but I need more S, more Z's. So A, okay, this is for A, run from like negative 1 to 1. Alright, negative 1 to 1. Yeah. Okay, so now I should have, okay, I need hold it. I should have 3 curves each side. Now I get it. Figure 3, figure 2, figure 1. I don't need figure 1. I need figure 3. Figure 3, I have 3 circle. One is this one. Okay, which is which? Let me just use 1. Here's a negative 1 to 0. Okay, negative -3. Okay, -4 to 0. Alright, -4 to 0. Then I have 4 curves. All of them they are in the left side. So I have four straight lines this side, and we will see what it is. Oh, I lost some. So why here displays so many numbers? What it is? 40. I need to erase. I need this one. Come on, don't display. Okay, run it. Like this. Okay, this is 1, right? This is 1, and all of those curves, they are circles inside. So things like this. This is the S-plane. Then go to here in Z-plane. It will like this. Here's a 1. Here's a 0. Yeah, like this. Oh no, need to show it. Yeah, things like this. So this is in the S plane. Looks like this. I take some lines in the left side. They are stable poles. Then go to Z domain. They are here. They are here. And then this side, obviously, they will be outside the unit circle. Outside the unit circle. Right. So this is the case, I will say, for continuous time system. For the stability, we will check the poles, whether they are in the left side or right side, right, in the S-plane. If anyone in the right side is unstable. And for discrete time system, we have similar result. Any poles outside the unit circle, that will make the system unstable. If all the poles inside the unit circle, okay, it's good, it's stable, it's stable. Right. So this is one thing. And then we can see this graph in a different way. In a different way. So like this one. This one, according to here, is what? This is S plane. This is Z plane. This one is poles with same zeta. I'm sorry. Okay, we check this case. This one, S plane to Z plane. In S plane, we consider all the poles along this straight line. They are all the poles with same zeta. Remember the poles, there's a negative zeta omega n plus or minus omega n times square root of 1 minus zeta square j. So all the poles. In a lot of cases, we need to consider poles look like this, right? Consider poles looks like this. So for same zeta, we will have straight line look like this. The next line will go to here, what the U will be. Okay, this one, imaginary axis will be here. Right? This is 1. This is -1. And this line will be something here. Right? Will be something looks like this. This one should be like this. Now we can have a look. Okay, this is a figure 2. Okay, I just work like this. Now S is this is zeta. Okay, I change this as zeta. Zeta from 0.1 to 1. Okay, by step 0.1. Step 0.2, okay. From 0 to 1. and I have several value of zeta. For every zeta, I have S. Okay, now it is S is a negative zeta times omega plus J times omega plus square root SQRT or SQR. SQRT, okay, square root SQRT, where the square root of 1 minus zeta square J times omega times square root. Okay, so this is the S. This is the S, and then we can have Z. Z should be same thing, just exponential power of S times T. And I need a figure. I need a graph, real S, and plot the real and image Z. Okay, I think that all the rest part will be same. Let me run it. Okay, it looks like this. Alright, it looks like this. If I add a 0 here, 0 should be the unit circle, right? Z is 0, zeta is 0, zeta is 0, then the real part is 0. We only have the imaginary part, right? Okay, so it is just this line. Yeah, from 0. Hold on, 0. Yeah. So the unit circle one is zeta is 0. Then we have one zeta is 0.2, 0.4, 0.6, 0.8 until 1. I should have 1. Oh, zeta is 1. When zeta is 1, this term is 0, right? Zeta squared, 1 minus zeta squared is 0. So we do not have an imaginary part. S should be a complex number, should be a real number. So this one, just this line. Yeah, this is a S. Then Z, S will be a real number. Then Z is also a real number. You can see both graphs. This is figure 3 and figure 2. Yeah, figure 2 is this one. Yeah, we have several lines. They go to the Z domain. They will be a curve looks like this. Right, curves look like this. Yeah, something like this. It will be something look like this. Okay, then the outside part, right? This is the inside the unit circle. If we look at the inverse way, we look at the other side. In this way, what it is, in this case, then here's this is a unit circle, right? This go to unit circle. Okay, so this part, this line actually is this line. This line is actually just this one here. Then this one will be outside. So it will be something look like this. So this line will be this one. You can have a look. That side, then zeta is positive, right? Zeta is positive. I just changed this zeta. Then there we go. Oh, too large. Yeah, W is 40 is too large. I use W is 4. Then have a look. Yeah, look like this one, right? This is this part. 4 is this part, and I give more. 4 to like 14. Yeah, 14 looks like this. 14 looks like this. When omega increase, this one finally will give you could go over the whole circle, and these curves they will turn around and larger and larger. Right, the circles will be larger and larger. We can just look at one. Zeta from 0 to point 2, 0.1. Then here I give 40. Okay. Have a look. Okay, yeah, now it looks like this. Turn around outside. Yeah. Okay, so this is the case if the poles they have the same zeta. And then similar we can have the consider the poles with S-plane, this one with some omega, some r, some distant r, some r. So this is the same. This is just omega, same omega, same omega, same omega n, same omega n. Then go to here. What it will be? This is a z domain in z domain, right? This is z domain. This one go to this one. Then a circle around it. It will be something like this, right? Something like this. Okay, now we can have a look. Do I need to erase it? I erase it. Okay, when you read the, okay, I keep it. Right, you erase, then you can't see it. Let me erase this part. No, not erase. Okay, then I keep these, but now I need a new part. This new part now is it will run for the same. Omega should be a fixed number. Omega should be a fixed number. So now I let omega is here's omega. Omega will run from some value like 0. 0.1 maybe too small. 1 to like 5. I choose 5 omega, and this one now omega now is the curve is related with zeta, right? The curve when you turn around this, the curve, this is the slope will be the negative zeta, right? Slope will be negative zeta, so this part will negative zeta omega n. So now zeta will run from turn around, right? That should be zeta. Okay, I use zeta like this part is zeta is run from 0 to 1. Zeta run from 0 to 1. Zeta from 0 to 1. Okay, this is zeta. Now for S, it is zeta plus negative zeta. Negative zeta omega plus j omega square root of square. Okay, zeta, now zeta is not a fixed number. Zeta is I need a dot on it, right? Zeta is a vector. I need a dot on it, and all the rest will be fine. And S, Z is still okay. All the rest part are same. Now after I running, I need by this way I need to erase this one. I don't need this. I don't need this part. Good. Otherwise, all the graph will merge together. All right. And in the beginning, close R. Okay. That'll be fine. line 62. Line 62. I have nothing here. I forgot something. Oh, here's the end. I can't give you this. Okay. Alright, looks like this. You see, this is in the S domain, and this one in the Z domain. In S domain, the center is original point. In the Z domain, the center is the point 1. The point 1. So they are still circles. So here's not circle. If I give more Z, now Z is from 0 to 1. If I give Z from how to define Z? If I want Z to turn around the whole circle. Okay, Z should be the cosine value, right? Z is a cosine value, so I use theta. Theta equal to from 0 to with a step this to 2 pi. Can I? Yeah, I use this as a theta, and then zeta. I use the cosine of theta. No, that is not this. So here, this is a cosine of theta. Cosine of theta. And this is square root of zeta squared. This is sine theta. Alright. Hopefully this works. Okay. Yeah, this is a circle. Right? This is in S domain. In S domain, it is a totally round circle, right? And after we give the related circles in the Z domain, there's still some kind of circles, but it's not so round. You see, not so round. Yeah, and the center is here. If we give more, now W is to 5, like to 15. What will happen? Oh, look like this. Here's a. Oh, this is original point. So all these curves, they will not go across the original point. It will turn around the original point. You see, the original point is here. So in the original point, it should be here. So all the curve will not go to the right side. Yeah, just turn around here. Okay. Yeah, this is another way to corresponding S and Z. Okay, then if I merge two together, okay, I give these again. I merge these two together. How to merge these two together? I want to consider this case. So S domain, the poles. Actually, in the design, when you design system, you are interested in poles here, right? Poles here, and with certain. This is omega n, right? Omega n. This is omega n j is here. Some omega n, right? Some omega n, and this one give you zeta, the theta. So, like this point here will be negative omega n times theta, right? We are interested in poles here, if poles in this side, the system unstable. We don't want, like, you design something, you try to find the parameter to make the system unstable. We don't do that. We're interested on the poles in this kind of point. And this side, in the below the real axis, they are symmetrically with the upper side. So we only need this part. Alright. So for this part, when we have curves, this one and this one, what can we see in the z domain? Okay. So this part, actually this part they are done. We do not need it again. Alright, so they won't work. Then we go to here. I want maybe I need two of it. I need two of it. So this part, we still need this zeta. Zeta now is run from not 0 to, okay, I need from pi over 2 to pi over 2 pi, right? 2 pi. I can write it this way. Yeah. Pi over 2 to pi. I need pi move out. 1 over 2 to 1 times pi. Right? I can work like this. So this one will give us a straight line with different zeta, also deal with round circles, right? Part of the circles. So omega is the same. This part is same. So figure 2, figure 3. Okay. To the end. Okay. Until here, we have all the curves. They are the curves with same omega n. And then next part, I want the part with same zeta. No, I don't need it. I copy from previous part. We have one part is just for fixed zeta, omega, right? This part. This part. Now, yeah, first part is for every zeta, we have a curve, we have a circle. Now is for every omega. That will become this. This time I need, for every z, I need a straight line. Okay, so just figure 2. Plot these. Figure 2. Plot these. Okay, what can we see? And it works. It's outside. Oh, I need a negative. Sorry, it's a negative. Here's a negative. Do it again. All right, it's this one. Oh, the omega 2 line. I don't need so many omega. You see, go around. Okay, omega. Let me let omega run to here. This is 40. Then half 20 will be here. A little bit less. I use 16, something like that. Okay, it's here, and I want more. So zeta now is run from 0 to 2. Okay, I run it until 1. Okay, zeta from 0 to 1. Alright, this is this curve. So finally we get this one. When you want to pick poles, you this is a design problem, right? Design problem. We know how to choose a poles in a continuous case, and then in this graph, like okay, so each one, this line, I go to the things look like this. This is go to the z domain. Z domain, here's a 1, here's a -1, then we have a unit circle, and then the curve word looks like this, and like this. This is a zeta equal to a fixed number. Fixed number. Zeta equal to this one. Zeta equal to some fixed number. I have several zeta, right? We have several zeta. Zeta from, this is zeta 1, 0.1. This is a zeta equal to 0. This is zeta equals 0, then 0.1, 0.2, 4, 5, 6, 7, 8, 9. This is 1. Zeta equal to 1. Okay, things like that. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, 1 is going down to the straight line. Yeah. So each one is give you a line. For example, you want to find a point with zeta is 0.3. You will pick poles. In the digital case, you need to pick a poles along this straight line. Yeah, you need to pick a pole along this way. And then for the omega, you see this line, this circle according to the omega. Omega, I give the graph. Omega is what? Omega run from not this formula 1. Omega is 1. Okay, omega 0 to 15. Omega run from 0, this is this point, this is -1 point. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if you want to find a certain the pole with certain omega, then you will check this line. For example, you want omega is 3, then okay, it's here along this line. Okay, good. Like here, this is omega is 3. Right. Then you can find your pole. You can find your poles. Like here is zeta is 0.2. Zeta is 0.2. All right, and this is 3. Okay, you can pick this point. You can pick this point. All right. Yeah. So it works similar as a continuous case, but in continuous case, the graph will looks like this. The graph looks like this. You pick a point here, pick a point here, then here you need to pick a point here. All right. Well, this method is this way is not so useful in nowadays. We have computer. We can even do it. We can have even more details just by some simple codes in the computer. We can get it. But in the early days, when you design something, you need this graph. Every time you just calculate, find the exact value, that costs more a lot of time. You can just pick a point from the graph. Yeah. Okay, so this is a relation between Z and S when you want to design system, design discrete time systems. Okay. All right. Then what else I want to give today? Okay, I think that's all for today. I still have some time, but I'm done. So see you next time. All right. See you actually next week. See you next week.